let's look at a couple more examples of calculating work. So let's suppose that we have 10 meters of rope that's hanging over the edge of the cliff. The linear density of the rope is 2 kilograms per meter. How much work do we need to do to pull all of the rope up to the top of the cliff? So I guess the situation is like this. Here's our cliff, and the rope is dangling down like this, and we're standing here, I guess, and we're going to pull up this rope. Now it seems like you could just find the mass of the rope and then multiply by the distance to the top of the cliff, but that won't work because every bit of rope that's hanging down has to travel a different distance to get to the top of the cliff. So there's no single distance we can use in our work formula. Since the distance is different for every bit of the rope, we're going to have to break things down into small pieces and then do some sort of integral. So with that in mind, let's see what we can do. Remember, if your force and the distance are constants, then the work is just F times your displacement, your force times displacement. But we need to break this down into infinitely small pieces that we can then put back together using an integral. And I want to do this two different ways. So one way to think about this is think about the situation when you have you've already pulled up some of the rope, say X units of rope. How much? Actually, let's do it the other way. Let's suppose that there's only X units of rope left dangling over the cliff. So you've pulled up some of the rope and there's only X units left hanging down. In this situation, what we need to do to make progress on pulling it up is to pull up a tiny bit of rope more. So we need to move this length of rope up an amount dx. As soon as we move this bit of rope up a bit, the very top of the rope we don't have to lift anymore. And so then the force that we have to exert changes because the rope that we have to lift got a little bit lighter. So we only need to make this length of rope move a distance dx. So the displacement is going to be dx in this case. But what is the force that we have to exert? Well, to lift something, we need to counteract the force due to gravity. And the force due to gravity is the acceleration due to gravity, which is 9.8 meters per second squared, times the mass of the object that we're trying to lift. So 9.8 times the mass of an object is the weight of the object. And that's the force that you have to exert to lift it, because you have to counteract gravity. So for this force, right, we need to counteract gravity. So we need to exert a force that's 9.8 times the mass of the rope. But since we know the linear density of the rope, the mass of the rope is the linear density times its length. So linear density is 2. And the length of the rope that we're lifting is x, right? We don't have to lift the whole rope. We only have to lift the bit of rope that's hanging over the cliff. So that part of the rope is length x. Just to check on the units, this 9.8, this is meters per second squared. 2 here, that was a linear density, so that's kilograms per meter. X is a length, so that's in meters. And dx is a displacement, so that's also in meters. And so putting this all together, we get kilogram, right? One of these meters cancels, so we get kilogram meter squared per second squared, which is a joule, which is what we were supposed to get for work, so this is making sense. All right, so this is the work to lift up, just to lift this length of rope, x units long, up a tiny distance dx. So we need to keep lifting so that the length of rope goes from 0 to 10. Okay, so we have to keep lifting it when the length starts at 10 and goes to 0. So, and we're integrating 9.8 times 2 times x times dx. And that's going to be our total work. 9.8 times 2 is, I guess, 19.6 times x dx. We're integrating from 0 to 10. Now we can integrate, so I guess I didn't need to have multiplied this out, because now when we do an antiderivative, we have to divide by 2, so we get back to 9.8 x squared from 0 to 10, and then plug in our bounds. We get 9.8 times 10 squared, so times 100, so that's 980 joules. Okay, so 980 joules to lift the rope. Let's analyze this another way. Another way to think about how we're breaking up this situation is what we need to do is just, this bit of rope here, we need to move it to the top of the cliff. And then this bit of rope here, we need to move it to the top of the cliff. And this bit of rope, we need to move it to the top of the cliff. So instead of thinking about lifting whole pieces of rope, we can think about lifting just tiny little specks of rope instead. So let's think about the work to lift the speck of rope at position X down from the cliff. So now we're going to use X to indicate how far we are down from the cliff. So what we need to do is multiply the force that we have to exert to lift that bit of rope by the displacement through which this bit of rope has to move. Well, the bit of rope that's X units down to the cliff, to get it back to the top of the cliff, we have to move it a distance X. So our displacement is just X. Now for the force to lift this speck of rope at position X, we have to exert a force to counteract gravity. So that's 9.8 meters per second squared times the mass of this little speck of rope. But the mass of this speck of rope is the linear density, 2 kilograms per meter, times the length of this speck of rope. But this speck of rope is infinitely short, so it's dx. And then to add everything together, we integrate this. So the total work is the integral, again from 0 to 10, of 9.8 times 2 times, I'm going to put up the x over here, times dx. You can see that whichever way you analyze this, you do get the same value for work, which is kind of nice. It's fortunate. For another example of analyzing a situation, let's look at a rocket launch. So how much work does it take to move a 1 metric ton rocket payload to an altitude of 200 kilometers? So we're talking just about the payload here. If you actually did this lifting, you must have some sort of rockets underneath your payload to get you up to 2,000 kilometers. This situation is tricky because we're going to start on the surface of the Earth, whose radius is about 6,000 kilometers. So we're going to start at the surface of the Earth and go out to a distance of 2,000 kilometers. And over large distances like this, the force due to gravity is not constant. So if you're near the surface of the Earth, the force due to gravity is roughly constant. But over large distances, gravity actually changes in strength. The further you get from an object, the weaker its gravity pulls on you. And fortunately, the physicists have a formula for that. The force due to gravity is, so classically speaking, this is what Newton figured out. It's a constant, which is called capital G, and capital G, the universal gravitational constant, it's the same everywhere. I think in standard units, it's 6.67 times 10 to the negative 11th. And there are some units associated with it, but if you're measuring things in meters, kilograms, and seconds, then this is the numerical value of G, times the mass of one of the objects. So in this case, it's one of the objects is going to be the Earth itself, so let's use m sub e, e for Earth, times the mass of the other object, which is going to be the mass of our payload, so I'll write m sub p, divided by the square of the distance between them. So this r here is the distance from our payload to the center of the Earth. So it turns out that we need to measure from the center of the Earth to make this formula work. Okay, well, we know the mass of the payload. It's a metric ton, so that's 1,000 kilograms. We're starting at, if you look at our starting position here, the starting distance of our payload from the center of the Earth is actually, well, it's 6,000 kilometers. And it's going to increase up to 2,000. So as our payload moves from where it starts up to 2,000 kilometers, this r changes, and so the force due to gravity will also change. So this force is not a constant as our payload moves up to an altitude of 2,000 kilometers. So we can't, to figure out how much work it's going to take, we can't use the constant equation for work. We have to instead break things down into small pieces. So let's find the work to move through position x, or I guess r is our variable here, so let's call it r. So r is the distance from wherever we're at down to the center of the Earth. Okay, so it's the force due to gravity, which is this whole formula, g times mass of Earth times mass of rocket, or mass of payload, divided by square of r, times the displacement that we have to move through to get through this single position. But that's an infinitely small displacement, so that's dr. Okay, so to get the total work, we're just going to integrate this. And we are starting 6,000 kilometers from the center of the Earth. We're going up to 8,000 kilometers from the center of the Earth. So we're going from 6,000 kilometers to 8,000 kilometers. G, mass of the Earth, mass of the payload, divided by square of r, dr. Everything in the numerator here is a constant, so let's pull all of those things outside of the integral. So g times mass of Earth times mass of our payload times the integral from 6,000 kilometers to 8,000 kilometers. I'm keeping the units here, by the way, because remember, for g to be the value that I said it was, you have to be measuring things in meters. So when we go to actually plug in our bounds, we're going to have to convert everything, all our kilometer values, to meters. Okay, after we've moved the constants outside the integral, we're left with 1 over r squared dr. Now we can integrate that. So g times mass of the Earth times mass of our payload. The integral of 1 over r squared, remember 1 over r squared is r to the minus second. And so use the power rule on that. We get minus r to the minus first. And we're going to go from 6,000 kilometers, which is 6 times 10 to the 6th meters, up to 8,000 kilometers, which is 8 times 10 to the 6th meters. And now we can plug in all these constants. Okay, g is 6.66 or 6.67, somewhere in there, 6.67 times 10 to the negative 11th. The mass of the Earth is 5.9742 times 10 to the 24th, and that's in kilograms. The mass of our payload is 1,000 kilograms. And now we need to multiply all this by 1 over, so 8 times 10 to the 6th minus 1 over 6 times 10 to the 6th. Okay. And then we can dump all of this into a calculator. Actually, let me work from the parentheses. So 1 over 8 times 10 to the 6th minus 1 over 6 times 10 to the 6th. So all of that times the mass of the payload, 1,000, times the mass of the Earth, which is 5.9742 times 10 to the 24th, times the universal gravitational constant, which is 6.67 times 10 to the negative 11th. Okay, and I dropped this minus sign, so this whole thing comes out negative, but I need another minus sign in front, which flips it all to positive. So I get 1.66 times 10 to the, let's see, 369 10. And this is in joules. So you can see this, just the size of this number hopefully gives you an idea of how much energy is required to lift things up into outer space. It's really a lot of energy. And this doesn't even count getting the object into orbit. This just gets you up to an altitude of 2,000 kilometers. If you, once you get up there, if you don't start moving sideways very quickly, you're just going to fall back to Earth. So this will get you into space, but it won't get you into orbit. Also, the radius of the Earth is actually a little bigger than 6,000 kilometers. So this is actually a slight underestimate of how much energy it would take.